Hey everyone, this is going to be a short video about tile-based rasterization, or lack thereof, in various GPUs. It's largely going to be an extension of David Cantor's look at this on Real World Tech, and uses a tool written by Nicholas Guillemot. I'm pretty sure I butchered the pronunciation of that name, but I'm going to link both the site and the tool in the description. And I also encourage you to watch Cantor's video to get a full explanation. But in short, Nvidia GPUs tend to use a technique called tile-based rasterization. It does exactly what it says it does. That is, the image is split into tiles and is rasterized one tile at a time. That helps improve memory access locality because you are writing to the same small set of data, the same small set of pixels over and over again, and you're probably also using a small set of data over and over again to render those pixels. If that set of data fits within cache, it's obviously going to help cache hit rates because you would load the data into cache, use it a lot, then load the next set of data, and repeat, as opposed to like bringing it into memory like constantly because you're missing cache because your data set is not fitting within cache. And I recorded this on another computer. This happens to have a Turing-based GPU. It's the same for Pascal. It's the same for Maxwell. I assume it's the same for Ampere, even though I've not seen it run there. I don't think Nvidia would have changed its technique since it seems to have worked very well for them for the past roughly half decade. Now, if we move on to AMD, this looks very different. So this clip was recorded on an AMD machine, on AMD-based GPU, specifically the one, the Ryzen 4800H. That's a GCN-based integrated graphics processor on a Renoir APU. And we can see that the pattern is very different. Triangles are drawn one after another, indicating that the rendering is proceeding in order. There is no tiling or trying to finish one section of the image before moving on. Curiously enough, if we select an image format that is larger, is more memory hungry, like in this case, if we select, well actually it doesn't matter which image format we select, then we can see that the work is like being distributed in tiles too, but this is definitely not the same as Nvidia. This could possibly help improve memory access locality at a lower level, but each of these tiles is going to be a lot shorter lived than, say, one of the tiles with Nvidia, where you finish drawing everything before moving on, so it's not going to be quite as effective. Now let's look at RDNA 2. So you can see here this is running on a 6900 XT. Again, we're going to see more of the same. Each triangle is rasterized largely before the next. Most of the work seems to be distributed in tiles. You can kind of see that here, but again, this is really the same as Renoir. The tiles are a bit bigger, but again, these are shorter lived tiles, and AMD is definitely doing less work in each tile before moving on, as opposed to Nvidia, where they're basically finishing rendering that entire tile before moving on. So again, Nvidia has a better strategy for cache locality. Now, that might also matter less if we look at a big picture, because RDNA 2 has a massive L3 cache. It's 128 megabytes on a 6900 XT, and could very well be enough to contain most of the data used to render the entire frame, and that would make tiling a lot less important, because you would still be keeping data on chip, probably inside that huge L3 or infinity cache. Now you might be wondering, okay, maybe it's still worth tiling to fit data onto the faster L2, but AMD's L3 or infinity cache already performs really well, so in terms of latency, it's very roughly comparable to Nvidia's L2. It's a little bit worse, but if you consider that a lot of accesses are going to be served out of AMD's L2 also, then the average latency to, say, absorb L0 or L1, latency after L0 or L1 miss might be kind of comparable anyway. And if we look at bandwidth, again, AMD has a much higher bandwidth L2. Their infinity cache bandwidth also is very high for being a L3 cache. And especially lower occupancies, it does very well. And you might be wondering, okay, why would you have low occupancies? Well, I mean, that's just the case, right? If you look at, say, like Cinebench rendering, at the tail end of workload, well, your tiles, you can kind of see like you get fewer and fewer CPUs utilized as the tiles finish up. Well, the same tends to happen on GPUs as well. And if you look at a frame from any application, well, in this case, this is a profile of Unreal Engine 5's city demo. And you can see that there's a lot of cases where you don't have full occupancy, and so performance at lower occupancy, so latency, the amount of bandwidth you can pull without filling the entire GPU, that kind of gets important too. So you can see stretches here where occupancy is really rather low. But yeah, anyways, I digress, so I'll end the video here. Hopefully you've learned something interesting today, and have a good one.